So this entire chapter has to do with what's called momentum. Momentum. How many people have played like backyard football before? Okay, maybe whether it's competitive or not, two-hand touch, tackle, whatever it is, right? All right, so if you wanted to tackle somebody that was bigger than you, okay? If you're tackling somebody that's bigger than you, or think about even professional football, where like a running back knocks over a linebacker who's much bigger than the running back. How are they able to do that?
Because they're fast.
How?
They have more momentum towards them. So, say the linebacker's just standing there. If the running back is going full speed at him and just hits him, he's going to fall over.
Yeah, because of his, what was the word used? Momentum. So in this chapter, we're going to talk about momentum. That's the whole chapter, it's about momentum. And momentum is really a measurement of an object's mass and velocity. It's really the product of them. So let's look at our first definition before we get stuff. So again, momentum is a quantity that describes a product of the mass and velocity of an object. So if somebody is twice as massive as you, and you're running at the same speed, well then they have twice as much momentum as you. But if I'm double the size of, say, one of my brothers, but he runs twice as fast as me, we have the exact same momentum then. So momentum, again, is directly related to mass and velocity, similar to kinetic energy. Kinetic energy was 1/2 mv squared. And kinetic energy we know is a function of an object's mass and the object's velocity. While momentum is also a function of mass and velocity. Are we all focused on the notes? Yes. We're all doing this, right?
Yes.
Okay. Now, the units for momentum. There's no simplified unit here. Remember how for energy, energy was really like Newton times meter, which became a joule, and watts were really joules per second. Well, in this section, there's no simplified unit for this. Okay, there's no simplified unit. Now, the question I always get is, why is momentum the letter P? Why is it letter P? Okay, and I actually write this down in my notes because I forget sometimes. First, Newton came up with momentum first. Okay, Newton simply called it quantity of motion. He actually called it I, little I. Then, a while later, another scientist, Leibniz, and he's another one of the famous mathematicians who studied calculus, one of the founders or the fathers of calculus, came up with the term P for progress. And if you think about the word progress, it makes sense. How much progress can you make? If you're moving something, the progress of it is really based on its velocity and its mass. Okay, progress. Now, there's something that we can derive from this formula. Now, if you want to, you can write it down, or you can just watch for a minute. Okay, so start with this formula, P equals mv. And let's consider the fact that, imagine an object is slowing down. So we're trying to find the change in the object's momentum. So the object's running really fast, and then it slows down, slows down, slows down. So my momentum is decreasing as I slow down. So if I want to find a change in momentum, I'm looking at the mass times the change in velocity. Okay, if I'm changing my momentum, my mass can't change. I mean, technically, I guess it could, right? If I'm running with like, say, ever see people run with a weighted vest so they can train for like marathons? Imagine you're running with that and you just threw the vest off. Well, then your mass would change, right? But we're saying that the mass is constant. So the only way that momentum is going to change is a change in velocity in this derivation. Okay? Now, if we divide both sides by the quantity time, and think of these as rates of change, okay, we divide them both by time, which is completely okay. If we do something to one side of the equation, we just have to do it to the other. What we notice is this. We get delta V over T. What's delta V over T defined as? Acceleration. Acceleration. So this becomes delta P over T equals mass times acceleration. But what else can I substitute in now?
Force.
Yes, very good, Jake. Way to go. Delta P over T is really equal to force now, because force equals mass times acceleration. So if we want to, what we can do now is multiply both sides by T, and what we get as a result is delta P equals F times T. This is called, and you should write this down, this is called the momentum impulse theory. Momentum from the left side, Delta P is momentum. The momentum impulse theory. And the momentum impulse theory tells me exactly this. I'm gonna highlight this as I go, okay? I'm gonna point. The change in momentum is equivalent to what's called an impulse. And an impulse, I'll explain a little bit better in a minute. An impulse is your product of force and time, but an impulse is really like what you feel. Okay, so let me give a quick example, something that would make it more obvious. Imagine this is a hard ball, not a tennis ball. Okay? And imagine you're at a baseball game, and you're in the crowd, and somebody ropes a line drive down the line. Okay, how are you going to catch the ball? Your bare hand, you're not wearing a glove. How are you honestly going to catch it? What would you physically do? Would you just put your hand down and catch it?
No, you have to
It would probably hurt a lot. Ed, ready, Ed? What would you do?
Well, you would go like that.
Why would you do that, Ed? Good, throw it back. So you would go like this. Or the ball's coming in, you would go like this. Soft hands. Why would you do that, Ed?
Well, I just know from like an egg toast that if you have like a harder surface, it's like a softer surface.
Uh-huh.
I don't know, that's how I've always been taught.
Did you grow up where there were like block parties and stuff?
I don't know, at my beach house, like twice a year they have like kids competitions and reigning egg toss champion with my partner, so.
We have to compete one day. So I told the other class when I was a kid we had block parties, and me and my brothers, it was always we were in the finals, two of us versus the other two every year. It was the same.
Yeah.
Because we knew like the idea of impulse. We knew, not physics-wise, but just conceptually or understanding it. So what's physically happening, right? If I catch it like this versus catching it like this, what am I doing? I'm doing something. I know I'm cushioning it, I know I'm absorbing the shock, but physically, what am I doing? And try to relate it to this idea of impulse momentum theory. Like,
You're sort of going with it, I guess.
okay, I'm going with it, good. So instead of catching it for like a millisecond, I'm catching it for a little longer. So tell me.
Are you like letting the momentum like decrease so it's not like as hard? Like you're letting it.
You're on the right track. One word is incorrect though, but you're on the right track. Something is decreasing, so it's not as hard.
It would be like less force because it's less of an impact on.
Why is it less force? You're absolutely right. So is force the word. You're letting the force decrease, but why? Look at the equation.
Because you're less because the velocity. Like they're.
No, because watch. Ready? I know what you're getting at. Ready? I throw this at 50 miles an hour. Somebody catches it. After they catch it, what's the speed? So it's still change in momentum isn't changing. This is constant. This is constant.
Is it because you're increasing the time?
Yeah, you're increasing the time period. Think about it. Ready? It comes to me, and I catch it. How long did it take me to catch that? It took like a millisecond when it hit my hand, right?
Yeah.
So all that force is hitting my hand in a millisecond, or maybe a tenth of a second, or whatever it is. Versus when it comes down like this, and I absorb the shock, it takes like a full second or two to catch it. It's the same thing a catcher's glove does. A catcher's glove slows down the ball over a longer period of time instead of just smacking into your hand. Like this would hurt a lot more than me doing that and actually absorbing the shock. So look at the equation. If you are slowing an object down to zero velocity and that object's speed isn't changing, so I throw a ball at you, you catch it first time, and then I throw it again at you at the same speed, exact same speed. That means that the momentum isn't changing. So, the change in momentum isn't changing. It's the same delta P in both cases. But the second case, when you catch it like this, you're increasing the time period of contact. So you're therefore decreasing the force. Okay, think about it logically. Let me give you numbers. It's a little easier when I use numbers. So let's say that the mass is 1 kilogram. The final velocity is 0. The initial velocity, I don't know why I'm putting parentheses. The initial velocity is 10 meters per second. Okay, those are the three numbers given. Let's say those we have. 1 kilogram, no final velocity, 10 meters per second. So if I wanted to find my change in momentum, okay, remember change means final minus initial. And that's a lowercase p, by the way. So lowercase p's. So my change in momentum is m times vf. This is from the last slide. or the previous scroll up. Final velocity is 0 no matter what. So the change in momentum is negative 10. Now, that's again assuming I throw it with 10 meters per second as my initial velocity, and you catch it and make it come to rest with a 1 kilogram object. The change in momentum is definitely negative 10. Now, ignore the negative for a minute, I'll explain that. If this is always negative 10, and let's say I go to catch it real quick, and I catch it with a force, or within a time period of 1 second, what would the force feel? What would the number be that has to go there to give me, what would it be? Oh yeah, or negative 10, but yeah, 10. Okay, that's the force I would feel on my hand. Now, instead of taking 1 second to catch it, the same exact scenario, but now I take, no, 5 is too much, that doesn't make sense, 2 seconds to catch it. What would the force now be? So what's happening is, as I'm taking more time to catch it, it's less force. Okay? Ignore the negative for a second. The negative is just indicating that you're pushing back against its motion. That's all. Okay, but look at the absolute value. Look at the quantitative, the magnitude. The magnitude here of the force you feel is 10. But the minute you use soft hands, it's called soft hands, right? And increase the time period of contact to 2 seconds, the force you feel goes down. Alright? At the end of the year, in the 4th quarter, we're going to do an egg drop project. And this is really the theory behind it. This is part of it. It kind of includes about 4 different topics in physics. Fluid mechanics, okay? It's going to include projectiles, it's going to include momentum, and then you could also look at potential and kinetic energy. So when you do this project at the end of the year, this is your thought process, okay? If the egg hits the ground like that, what's going to happen?
Splatter.
Yeah, it's going to splatter. So your goal is to absorb the shock. So you might use springs, and we'll talk more about springs when we get to Hooke's law. But the end of the year project really ties together like 5 different topics we're going to learn. This is one of the key ones here, to increase the time period of contact. So when your egg drop design lands, this would be a terrible design, but imagine there's an egg in here. When it lands, it doesn't just go, right? There's something that's going to absorb the shock to make it kind of cushion. So there's some sort of springs there or something that's going to make it absorb. That's for you to think about. Okay, but just keep that in the back of your
If
head.
it cracks, is it like pass or fail if it doesn't crack?
It's not pass or fail. If it cracks, you get the lowest grade though. So what I do is I put you into categories. If it doesn't crack, you're in category 1. If it does crack, you're automatically in category 2. But if it doesn't crack and you land in the landing zone, you're now in category 1A. If it doesn't crack but it misses the landing zone, you're in category 1B. And 1A is the higher grades, 1B is the medium grades, the last grade is the lowest grades. Okay, but it's not pass or fail. But if it doesn't crack, you're going to end up getting the lowest grade.
Do you have to create like a slingshot or something, or can you just swirl into the landing thing?
You need to create what's called a chassis or an object to hold it, so that when it lands, it doesn't break. You get to build anything you want. I have a lot of rules and restrictions, but we'll get there. I'm not, for the sake of time, I want to keep going. But we'll do it in the 4th quarter. This quarter, probably at the end of this chapter or maybe in the beginning of the next chapter, we're going to do a catapult project, which uses potential, kinetic energies and stuff. Okay, that'll be the 2nd quarter project. All right, anyhow, what we're going to do with this idea of momentum. So let's look at the first example. What velocity must a bullet with a mass of 4 grams have in order to have the same momentum as a bowling ball with a mass of 6 kilograms traveling with a velocity of 8 meters per second? These are reasonable numbers. 6 kilograms is about 14 or 15 pounds. That's about a bowling ball size for professional bowlers or real bowlers. I know you might use, like 8 or 10 pound ones when you bowl for fun, but they're about 15 pounds. A bullet is about 4 grams, okay? And a velocity of a bowling ball of 8 meters per second is what you would toss down the lane. So let's come up with the velocity of the bullet so that it has the same momentum. Look at the mass of the bullet. It is so small. What is the mass of the bullet in kilograms?
0.004.
Yeah, it's 0.004. The mass of the bowling ball, though, is 6 kilograms. Since the mass of the bowling ball is significantly larger, what can you conclude before doing any math about the velocity of the bullet? A much higher velocity. And think logically. A bowling ball traveling pretty slow, it still has a lot more momentum than a bullet. Okay? So we have to look at this and realize that the answer we're going to get for v, what would it be? This is the velocity of the bowling ball, v2. It doesn't matter. If I call the bowling ball, this is the bowling ball, right? This is the bullet. Okay, so the bowling ball's velocity is 8 meters per second. The velocity of the bullet is what's unknown. Now, you can go ahead and you can find the momentum of the bowling ball, set it equal to the momentum of the bullet, and solve. Or you can just set the formulas equal. Please make life easier on yourself. So say the momentum of object 1 equals the momentum of object 2. This is not final and initial. Again, this is not final and initial. 1 and 2 are the objects. The momentum of object 1 is the mass of object 1 times its velocity. The momentum of object 2 is its mass times its velocity. My goal is to find out the velocity of the bullet, which is object 1. Okay, so solve for V1. Again, no need to actually get any of the momenta for these two. What's important though is that you get the velocity. So ignore that intermediate step. Don't find the momentum just for no reason when you could solve algebraically. What do you get? $12 something. It's got to be a 12 because I see 48 in the numerator and I'm thinking 4 in the denominator. 12,000? Okay, so think about this. A bullet has to travel 12,000 meters per second in order to have the same momentum as a bowling ball that's traveling down the bowling lane. It really, really emphasizes the importance of mass when you're looking at momentum. Okay? So again, that's a simple example, okay, of how momentum can be the same between two objects of different masses by having different velocities. Okay? Alright, let's look at the second example. We're looking at a car that's 1,500 kilograms mass and it's moving with a velocity of 20 meters per second east and it collides with a tree. So it's traveling east, it hits the tree head on. And it takes about 2 seconds for this tree to come, or for this car to come to rest. And the question is, find the force exerted on the car. Okay, find the force exerted on the car. So let's take a look at this problem here. We've got, first, a mass of the car. And I call that M1 at first, but I realize that there's no other mass, so I can just call that mass instead of M1. I've got the velocity of the car before the collision, so what do I call that? Before the collision? Louder. Initial velocity. What am I trying to figure out in the problem? Force. I know the time period it takes for it to come to rest is 2 seconds. What about this? What's VF? Why? Because it comes, yeah, you're exactly right. It comes to rest or it comes to a stop. Okay? Obviously, you would probably hit the tree, front end would probably wrap around a little bit, and the car would maybe wobble for a minute, but it comes to rest, maybe it has to stop. So that's what I know. Now, I can start with momentum and say mv and look for momentum. But when I see that there's a change in velocity and I see that there's a force involved in the problem, what should I probably use? What theory? F times? Good. Okay, delta P equals F times T. The change in the momentum equals the impulse. Remember, Ft is impulse. Impulse, the momentum impulse theory. Change in momentum means final minus initial. What's the final momentum going to be in this problem? What's the final momentum going to be? What is it?
0.
How come?
Because final velocity is 0.
Yeah. Final velocity is 0, so that's got to be 0. So this reduces to make it simpler. Now remember, momentum is equal to mass times velocity. I want to solve for F. That's my goal. So go ahead and divide by time. Okay, go ahead and divide by time. What do you notice? What kind of an answer you're going to get? Don't give me the number, but tell me what kind of an answer.
It's gonna be negative.
How come? I'm traveling east.
Well, because the force is pushing back on.
There it is. The tree pushes back against you. Exactly right. I'm traveling east, and if I'm going east, the tree has to push me west when I hit the tree. So the force has got to be negative in this answer, and you're going to notice you'll get a negative answer. What do you get? What do you get for force in this problem? It's a large number, Kat.
Is it negative 15,000?
Yeah, 15,000 units for force are newtons. Now, let's go through a little public service announcement.
Shout out to Jay-Z.
No, shout out to not ever even considering drinking and driving. Think about this for a second, seriously. 20 meters per second traveling in a car. It's not even that fast, okay? Now, you hit a tree or a sign or something, 2 seconds, that's a reasonable time. In reality, actually, probably only 1 second. So this number would probably be even larger. Somebody do me a favor, go to Google, convert. Convert 15,000 newtons to pounds. Type in 15,000 N, and then the word 2, and write LB for pounds. Tell me what you get in pounds of force that you're going to feel from something like this. How many pounds of force
A
is
lot.
your car going to feel? What do you got?
372.13.
Yeah, 3,000 pounds of force on your car. Now, granted, thank God we have airbags, because airbags, what do? They increase the time period of collision. You hit the airbag and it's increasing the delta T. So you don't feel as much force as that, but you're still going to feel a good chunk of that force. 3,000 pounds. In case you want to wonder, 100 pounds is a decent amount of weight to lift. Imagine 30 times that on your body, what's happening to you. That's why you also need to make sure you buckle up when you're driving. I know people don't buckle all the time, not you, but people in general. It's kind of scary to think about that. Why would you not buckle your seatbelt? It's like saying, kill me, please. If I get into an accident, you go through the windshield, you're going to be going through the windshield feeling this force on you from the windshield. If you don't think glass is going to cut your body up from that, you're in another world. Okay, so seriously, think about this for a second. It's kind of crazy. That's the kind of force you would feel. All right, the numbers are actually reasonable. This is a reasonable mass for a car. That's what would actually happen. Okay, so please, I'm not joking when I say this. I know some of you are like, oh, it's a lot. But no, seriously, okay?
But we don't live in the city, so.
I know, and I know a lot of you have your drive. Well, once you're 21, once you're an adult, once you're drinking, people do stupid things. I can't begin to tell you how many friends of mine I have that are complete morons that will think that, oh, it's okay, I just had a few drinks, it's not a big deal. Forget the whole, I'm going to get, driving under the influence and get arrested. How about your life, I'm going to pause. All right, so example 3 says a half a kilogram soccer ball is moving to the right with a given velocity. It hits a wall and it bounces off. Yeah, half a kilogram, that's like a pound or so. It's about the weight of a soccer ball. It bounces off the wall, rebounds, and the wall exerts a force of 42.5 newtons on the ball. Okay, for a time period of contact of 0.2 seconds. Find the velocity of the ball after it hits the wall. So the rebound velocity. Now, what was that theory that we learned? Way back on Friday. What was the theory that we learned?
Change in P equals FT.
Yeah, what was it called? Change in P equals FT. What's the name of that, Catherine? Good. Momentum impulse theory. So, whenever you're given a problem that has a change in an object's velocity and there's a force involved in it, there's a good chance you're going to end up using the momentum impulse theory. Okay? So let's start by listing what we know. The mass of the soccer ball is 0.5 kilograms. The initial velocity of the soccer ball is what? Yeah, 9 meters per second. What are we trying to find? Yes, VF. Remember, we're trying to find the velocity of the ball after it hits the wall, which is final velocity, after the interaction. Now, if the ball is traveling this way, right, with 9 meters per second as a velocity and it hits the wall, which way does the wall push? So what kind of a force is it? Negative. So let's list F as negative 42.5 newtons. Okay, negative 42.5 newtons. In the time period that the wall is in, or the ball is in contact with the wall, is 1/5 of a second, which is pretty reasonable. Think about it. You kick a ball into the ball is not physically touching the wall for any more than this amount of time. If anything, it'd be less than that amount of time, but it's not going to be greater than that. The ball doesn't actually hit the wall, stay on the wall for a second, and then come back. It comes back pretty quick. Have you ever seen a time-lapse video with a high-speed camera of somebody kicking a soccer ball or bouncing a basketball? Have you ever seen the deformation that occurs? It's kind of cool, actually. Remind me at the end when we're done with this, when you guys are working on that worksheet, I'll bring up a video to show you. But if you dribble a basketball, it actually deforms a good amount. So when you kick a soccer ball and hit the ball is hitting the wall, okay? And it's actually doing this, deforming a little bit before it comes back off the wall. It has an elastic nature to its material. It's made out of a soccer ball is made out of a rubber, but it's pressurized with air inside of it. But it can still fluctuate if enough force is applied to it. So we're going to talk about not until section 6.3, but we're going to talk about what that means. If an object's shape deforms as a collision occurs, as opposed to imagine billiards or pool. Are you playing pool? You hit the cue ball into another ball, they collide, and they separate usually. There's no deformation. Those are fixed shapes. If there's deformation, it's microscopic or on the nano level, tiny. There's no change in the diameter of a pool ball. But something like a soccer ball or a football, if somebody kicks a football, right, it's going to deform as they kick it, as they punt it. So we have to consider this as we're approaching these problems. Now, we're trying to determine the final velocity of the ball, so let's use the momentum impulse theory. The reason being, we have time and force, and we know that delta P uses M and V involved. So we start with delta P equals Ft. Okay, we start with delta P equals Ft. What can I put in for delta P in this problem? What does delta P mean? Again, delta means change, and so it's change in P, and P stands for momentum or progress. Very good. Good memory. What is the formula for P? P equals? Yeah, mv. So if I want to change, it's final minus initial. All right, so this is our approach. Here's our approach in this problem. Now, our goal is to find VF, so we can simply add MVI over and then divide by M. Please don't try and cancel M. M doesn't cancel in this problem. You can factor M out and then divide by M and solve, but it doesn't make the problem any easier, actually. So add the MVI to both sides. And then divide by mass. Okay, solve algebraically whenever possible. Solve algebraically whenever possible. Let's plug in our numbers now. The force applied is negative 42.5 newtons. Over a time period of 1/5 of a second. The mass is 1/2 kilogram. Initial velocity is 9 meters per second. All over the 1/2 kilogram. Bless you. What kind of a number should you get here? Don't give me the answer, but what kind of a number? Why, Victoria?
Because the force is negative,
Okay.
and because the velocity is moving.
I don't know. Because you're being pushed back.
So the force is still negative and it's being, so which way is the soccer ball moving afterward? The motion of the ball, okay? It's going this way with positive velocity. It hits the wall and it comes back off the wall. Well, if it comes back off the wall, its final velocity has got to be negative. A lot of you forget to do this on your tests and on your assessments. When you get an answer, check the sanity of the answer. Does it physically make sense? Is this a reasonable answer? Okay? Is it reasonable? What do you get for VF? Negative? Negative 8? Agree, disagree? Yeah? All right. We'll take it. So, in the end, the object hit the wall, bounced back, at a lower velocity than it hit the wall with. Keep that in mind for section 6.3. When we get to section 6.3, we'll talk about what that signifies. If an object rebounds off the surface, but it doesn't come back off with the exact same velocity, it means something about it. And you can think logically if you want. I'm not going to talk about terminology yet. But if you drop, like the bouncy balls? We talked about bouncy balls at one point. If you drop a bouncy ball, does it ever come back up to the height it started at? Why not? Some form of friction, whether it's air resistance slowing it down, whether it's the object deforming as it hits the floor and squishing and coming back. It's some sort of loss of energy, really. Okay, and we'll talk about what that loss of energy implies. And in physics, we call that inelastic. But I'll talk more about that in section 6.3. Okay, had this number been negative 9 as an answer, it would have been what's called an elastic collision. All right, so let's keep that in the back of our mind. We don't need to know it yet. All right, example 4 says a 2,000 kilogram car traveling to the east, or how about just east, sorry. Traveling east. Okay, traveling east slows down uniformly from 25 meters per second to 10 meters per second. How long does it take the car to do this if the force on the car is 750 newtons? How far does the car traveling during this deceleration? Now, how long does it take? So first we're looking for what? Time. So if you think about the impulse momentum theory, you have time as one of your missing variables in it. You have a force that's applied to slow it down. If the force is slowing it down, what do you know about the force itself? Yeah, its magnitude is in the negative direction, really. Okay? It's a magnitude of 750, but it's in the negative direction. So we've got initial velocity, final velocity. We've got a force that it feels. And we've got a time period that we're looking for. Okay, we also have the mass. Okay, we also have the mass.
In these problems, is the force like almost always going to be negative because
Sure, but I mean, you could have an object at rest that's kicked by a soccer ball and it accelerates it. So the force would be positive. Right? It doesn't have to push back. This example happens to have one where it's pushing back because it was slowing down and it hit the wall. But if an object's at rest, and I want to see with what velocity it goes to, if I keep it with a certain force over a certain time period, it'll be a positive velocity, a positive force, and always be positive energy. So it's all context, okay? It happens to be both negative though, yeah. So we can use delta P equals Ft. We could say mvf minus mvi equals F times T. Okay, remember delta P means final minus initial. So I'm jumping right to mv there. I'm not writing Pf minus Pi every single time. Our goal is to find out how long it takes, so we should divide by. A simple problem. Again, part A is quite simple for this one. We're looking for the time it takes, we divide by force. What kind of an answer are you going to get if it's time? It's got to be positive. So if you forgot that negative for the 750 in the bottom, then you'd probably get a negative answer and say to yourself, what did I do wrong here, right? So this is 2,000 times final velocity, which is 10 meters per second, minus 2,000 times initial velocity, which was 25 meters per second. So both the numerator and the denominator are negative, therefore you get a positive time, or amount of time it takes for this to occur. How much time does it take for this to occur? 40? Others agree? 40 seconds? Now, part A was pretty easy, but I want to do the follow-up for part B. Part B ties into play. Well, you know what? Let's think about this realistically now. How far does it travel, or what is the stopping distance for this car? So this might be where might something like this be used? Why might you study a problem like this? I mean, it's a car, right? So let's think about vehicls. What do vehicles sometimes get into? Accidents. All right, so have you ever heard the theory before, if you get rear-ended, it's always the other person's fault if you get rear-ended?
Yeah.
Okay, which is for the most part true, but there are extenuating circumstances. So if you wanted to see, for example, say somebody was just on the side of the road or the right lane broken down and you didn't see them far enough and you said, but I wasn't going that fast, I slammed on the brakes, I wasn't speeding. And they're like, no, you were definitely speeding. There's no way you could have skidded this far. Well, this is an exact example of that. You can actually figure out the force applied by the brakes is. You could then solve to figure out the time period in which you were braking. Now, if you're given the velocity, somebody says, I was only traveling at 50 miles an hour, you can say, you know what? Even if you were traveling at, say the speed limit is in New Jersey, say it's 65 miles an hour. Even if you're only traveling at 65 miles an hour, you could still say to them, well, you know what? The stopping distance would be too short or too far. So if you look at the skid marks on the road, you could determine the velocity at which the person was traveling to see if they were breaking the law or not. So if they were traveling with too high of a speed, they can get a ticket, or they're then found accountable for it. So let's figure out how far it's traveled during this deceleration. What formulas from the beginning of the year might I use to find the distance traveled? To find the distance traveled. Guys, focus. A lot of you are giggling. A lot of you are looking at others' iPads. Okay, I don't want to have to deal with anything right now. Focus.
Is it x over t?
That's not always work. That only works x over t to find velocity when you don't have acceleration. But clearly we have acceleration.
Okay, that was thinking velocity over time.
Okay, but we have acceleration.
X equals v to the squared plus 1/2 a t squared.
Okay? We can go with this one. There's two options. There's this one, there's also another option. What's the other option to find displacement?
Vf squared equals vi squared plus at.
Close. AT is when they're not squared, yeah. It's VF equals VI plus AT when they're not squared. So we have two options here. Now, look at both equations. In the first equation, we know VI, we know time, we don't know acceleration. But in the second equation, we know VF, we know VI, but we still don't know acceleration. So neither of them is better than the other, except for the fact that in the first one, x is already solved for, right? And our goal is to figure out the stopping distance. So we're looking for x. So let's choose the first of the two to solve for, but both would be applicable. Now, to use this equation right here, again, we've got VI, we've got time, but we don't have acceleration. How could I find acceleration in a problem like this? There is more than one answer to do it. Kier? Yeah. One way to do it is this, right? F equals ma and solve for a. The force applied is given. The mass of the particle or the object, the car, is given. So we could do that to find out a. What's the second way to find, Paul, acceleration? Were you going to do the same way? Okay. You know the second way? Yeah. A is defined as the change in velocity over time. Either way works. So we're going to use this original formula up here, the first one, to figure out the stopping distance, but we can apply either of those in there. You get the same answer. It really doesn't matter. I'm going to use F over M. Okay, it was the first one suggested, so I'll use F over M. If I plug in my numbers, VI was 25, time was 40, plus 1/2. What was the force? Negative what? Negative 750 over a mass of 2,000? So let's see if this answer is reasonable, or what we can do to change, or what we can do, or what we can think about in the context of the problem. Right? If X is really small, it means you probably have really good brakes. If X is really big, your brakes probably aren't that good. Or maybe you were just traveling too fast initially. Okay? So what do we get for an answer for X? Come on, I see calculators out. I don't see them being used. Use your calculators. Let's go. And please stop using your calculators and your iPads. I know it's good now, but when on the test you make a mistake because you don't know how to use your regular calculator, it's kind of sad. What do you got, Jake? 999.97. So you got 1,000 meters pretty much? Can others check to see what they got? Say again? 1,700?
I got Jacob.
You got 1,000? It's probably 1,000 then. I don't know, my answer's in the other room. That's why I'm asking. Sure. Let's just say it's 1,000 for now. Let's talk about the context of the problem, though. It's more important. 1,000 meters. Mike. Only that one, unfortunately. Yeah. The other one, somebody broke the thing when they let it come crashing down last year. Unfortunately. 1,000 meters. What's 1,000 meters? How far is that? Yeah, that's a kilometer. Thanks. Very true, Paul. Good point. It's a kilometer. It's a little bit less than a mile. A mile is around 1,600 meters. So this is over half a mile to stop. So either one of two things. The force that's applied needs to be greater, so this person needs to get their brakes checked, or they were traveling too fast to start. You can check if they're traveling too fast by looking at the initial velocity of 25 meters per second and converting that to miles per hour to get an idea of what that is, on a realistic scale that we would use. When you get an answer, think about the context of the problem and what it's asking. Thank you, Marianne. I didn't know that's what you were referring to. Yeah, this should say 40. And did you use 40? And you got 700? Okay. So let's fix that. It does sound more familiar. I apologize. I wrote .40. I don't know what I was thinking. 40 seconds was the time it takes for this car to stop. Okay, 40 seconds, which in itself is too long of a time, really, right? If you slam on the brakes, would you want it to take 40 seconds to stop? Probably not. I mean, that's a little bit long. 40 seconds? That's really... Oh, it's very long, yeah. Now, again, I keep saying you slam on the brakes, but maybe this problem, the person was just slowing down gradually. It's possible that they saw traffic way ahead and they started slowing down earlier. So they slowed down with very little force. So maybe they didn't push the pedal down too hard on the brake, which is why the force is only 750 newtons. Thank you for the correction. So example 5 says, if the coefficient of kinetic friction between a 2,300 kilogram car on the road is 1/2. That's our mu k. Then what is the minimum stopping distance for the car when it's moving at 29 meters per second? Okay, 29 meters per second. Now, before I solve this, what's one way of solving this that we've done before that's not using momentum? What theorem can you use from the last chapter? Last chapter that might help us.
Work kinetic energy.
The work kinetic energy theorem. So, I encourage you, if you want to check, you can go ahead and use that as well to see that you get the same answer. I'm going to do it with momentum, but I want you to understand that either way works. Now, when it comes to the midterm exam, and you have the mathematical questions at the end of the exam, you choose what method works best for you. So in this problem, there are 2 ways to solve it. So if you don't like momentum impulse theory and you want to use work kinetic energy theorem, that works as well. Okay? So let's use the momentum impulse theory to show that it's true. My initial velocity, in this case, what's my initial velocity? Not 0. What is it? Why? Why is it 29? Why is VI 29? And then what's VF? Yeah, VF is 0 in this problem. Again, the car is traveling, then the brakes are applied, and then it comes to rest at the end of the problem. The mass of the car is 2,300 kilograms. Mu k is 0.5, and that is unitless. So if we want to find out the minimum stopping distance, and it's only traveling in one direction, we're really trying to find out what x is. That's our goal. Now, if you use the work kinetic energy theorem, you'd be saying F times D times cosine theta equals delta KE, and you find D for minimum stopping distance. I'm calling it X right now, because again, I'm moving in one direction only. So my X value and my D value will be the same. If I want to find X, like I did in the last problem, I'm going to probably have to use X equals VIT plus 1/2 AT squared. But the problem is that I don't have time. Okay? I don't have time. So let's find time. Does it make you feel smarter when you just type real quick and go ahead? So, all right, easy. So, the momentum here, or the change in momentum, there's no final velocity. Okay, so it's going to be really just 0 minus mvi. Zero minus mvi. There's a little trick to this problem, though. There's a little snag, I guess you would say. We don't have the force in the problem, but what is the force that's acting on this? What kind of force? Friction. Kinetic friction. And kinetic friction can be replaced with mu Fn. But friction acts against motion. So what kind of a force is it? It's going to be a negative value. Now, if I just go ahead and do this, okay, the 0 drops off, obviously. And then I replace Fn with mg, as we know it's true, when an object is moving horizontally. The problem we're going to get is that we didn't even count the fact that the force itself is negative. By replacing Ff with mu Fn, we're kind of ignoring the negative component of its nature. So to solve a problem like this using the momentum impulse theory, we need to apply a negative sign to our force in this problem. So go back up here. This is a negative force. Okay, so the negative is going to carry down. So we want to solve for time, guys. Stop. Focus. We want to solve for time. Divide by mu mg. Divide both sides by mu mg. Masses cancel and the double negatives become positive, making your answer much more simple than you would think algebraically. It's just VI over the product of mu g. So what do you notice in a problem like this? The time it takes is independent of the object's mass. Okay, now, let's pause for a second and think realistically. This problem is assuming that you can apply a force to stop the car with whatever force you like. But your brakes have a limit to the force that they can apply. So an object like an 18-wheeler that's extremely massive, traveling with the same velocity as a car, it's not very massive, will definitely take longer time. Because the force you can apply at F will not be the same really. Right? So again, the mass of the object, in essence, does really affect the problem, although we're getting a solution that is independent of the mass. Okay, so think about the problem itself after you simplify and cancel things out. So the time it takes for this object to stop, what do you get for the time? I think something's off. Make sure you multiply your denominator together first. Put parentheses around your denominator. It's 29 over 4.905. So it should be around like 5 or 6. 5.91? What mistake did you make? What was the mistake?
I did 29 divided by 0.5 times 9.81.
Yeah, you need parentheses around your denominator, folks.
I did,
Oh, so that's not meters per second. So that's the time it takes to stop. Is that right? That's the time it takes to stop. Let's now find the distance traveled before it stops, which was what we were trying to figure out in the beginning. X equals VIT plus 1/2 AT squared. You know the initial velocity is 29 meters per second. You know the time is 5.91. But you don't know the acceleration in this problem. So we again apply the same exact approach as the last problem. Okay, remembering that acceleration is either force over mass or delta V over time. I'll use delta V over time this time just to mix it up. And what do you notice what happens if I use a generic solution with delta V instead? Makes the problem all in terms of what? It's definitely negative, yeah, absolutely, because VF is, VF is 0, so this drops off, making this VIT plus 1/2 negative VI over T squared. But you'll notice that the time cancels in one of the spots, and it makes everything a function of initial velocity and time. This time cancels with one of these times up in the numerator, making the problem VIT plus 1/2 negative VIT. Okay, the cancellation is actually pretty cool, the way you only get only VI's and T's in the end. So I have a VIT and I have a half of VIT subtracted from it. It leaves me a half of Remember, this is like saying you have one apple and then minus a half of an apple, well, that leaves you with a half of an apple. So the algebraic solution is actually just this. That's the algebraic solution. So if you were to simplify and not plug in numbers, that's what you would end up getting algebraically. But again, if you want to plug in numbers, you can plug in numbers as early as the step right here. Okay, you can plug in your VI with 29 times your time, negative 29 over your time, times your time squared, and you can get an answer. Either way, you get the same solution. Okay? What was the number in meters that you get for this? I think it was like 50 something, if I recall correctly. $55.85? Oh. 85.65? Others agree with that? All right. I was thinking 58. Isn't that funny? Because it's 80 and it's 85, the way the numbers I had it back. I taught this lesson in the other class. It was last week. I just don't have my answer key. I'm thinking about it. I'm like, I thought it was 58. So 85. Okay. Just to give you a heads up. Okay, there are 7 problems. There are 7 problems. So, let me think. Start it tonight for sure. It'd be tough to get it done. I mean, you could definitely do it for tomorrow. It would just be a little long. Let me see how far we get through 6-2. And I'll decide. Maybe I'll make 6-2 due tomorrow because that's only 2 problems. And then I'll give you another day or two for this one. Let me think about it, okay?